Okay, guys, so gonna talk about these pressure changes with altitude. Okay, so we're gonna start from this very beginning. Okay, so this is the change of pressure regarding altitude, that is y. Okay, and it's gonna be equal to minus density times the acceleration. Okay, so this equation comes from a force balance that I'm not gonna show here, but it's gonna be in another video. Okay, so from here we have several cases that I want to discuss today. Okay, so first thing I'm gonna say, well, take a look at this. I'm gonna take that if you go down, this y is gonna be negative, and if I go up, this y is gonna be positive. Okay, this means that if you see this equation, therefore this delta p is gonna be negative, and this delta p is gonna be positive. Okay, this is just a thing with this minus sign. This minus sign can be here or cannot be here. Okay, so I'm gonna put it here just because of it simplifies interpretation. But if it's not here, this minus, it's the same equation. You shouldn't worry. Okay, but you need to interpret a little bit different the results. It makes sense that if you go up, for example, in the atmosphere, if you go up, so pressure is going to go down because you have less atmosphere above you. And if you go down into the sea, for example, you're going to go and see the bottom of the sea, so pressure should be increasing. Okay, so in this case, this minus sign helps me for this interpretation. But if you don't have this minus sign, there's not much of a problem. You still can do this type of thing. Okay, this means that, for example, if you go like this, okay, so if I increase the depth, I go negative and lower y, or higher negative y, this means that delta p should increase, and this one over here, it's gonna be rho g. Okay, so this is the first case that I want to explain. So let's say that density is constant and g is constant. So if I take this as assumptions, this means that, okay, so this is going to be like this: dp dy equals to rho g, sorry, minus rho g. Oh my god, again, I was saying a lot about this minus sign, and I don't write it. Okay, so minus g. Okay, so you need to separate variables, and if you do that, you got yourself dp equals to minus rho g dy. Therefore, you integrate here and you integrate here. If you want to put something here, well, you can put P1 to P2, and you can put Y1 to Y2. You can do that. But nonetheless, this result is very simple. This is just delta P equals to minus rho G. And we most of the time, we call this minus rho GH. But if you want to be really, really specific about it, you can do minus rho and then y2 minus y1, and that's kind of the same thing. So this one is called the hydrostatic equation. Okay, so that's the name of this equation. It means that exactly this. Okay, so this is a behavior of pressure with going into the sea. Okay, maybe it's not altitude in this case, maybe it's just depth. Okay, so maybe for depth you can think about this as going down and down. Okay, but it's kind of the same thing. Whether you're going up or you're going down, you're gonna suffer pressure changes. And in this case, it's a very linear situation. Okay, it's called the hydrostatic equation, not because you're working with water, but it's because you're working with a liquid. Rho equals to a constant means that rho is rho equals to a constant. Oh my god. So rho equals to a constant actually means that you are with an incompressible fluid. Okay, so that's about it. Let's just go with another case. Let's just complicate things here. And so I'm gonna begin again with this one. This is my very first beginning. Okay, but now I'm gonna say, though, instead of this thinking that it's a constant, I'm gonna say, well, you know what, it's not constant, and I need then a model, and this model is called ideal gas model. So you know this thing. Okay, maybe you know it from thermodynamics basic courses. So this ideal gas thing, just a model for the density, and it's changing with pressure and it's changing with temperature and so on. Okay, so if I substitute here, it's gonna be like this, and I'm gonna put the p here. I'm gonna go fast with this one. So what I'm having here is g rt and then dy. I have already separated the variables. You can do it. It's just algebra. So you're gonna integrate here and you're gonna integrate here. Therefore, this integration is really simple. So you're gonna get logarithm p2 p1, okay, equals, that's the left side, and this was going to be minus grt. Everything is constant here, all these guys are constant, and therefore you're going to then y2 and y1. Okay, so in this case, I'm just going to arrange this a little bit. So it's going to be p2 p1 and then the exponential function minus grt multiplied by y2 minus y1. Let's say that y1 equals to 0. Okay, let's just start at the surface of the earth. Let's just start at sea level. Okay, so in this case, this one is 0. Let's say that then if this is happening, so P1 equals to 1 atmosphere, and therefore you have yourself this very first, you can call it boundary conditions or the first statement for these ones, and then you have P2 equals to P1 and then the exponential minus g rt and then just y2. Okay, so if you go up, okay, you need to see that this one is 1 atmosphere, this one is going to be lower because this function over here, if you start increasing this variable, so it's going to give you less and less of this of value. So if you want to do certain mathematic assumptions, let's just try, for example, let's just say y2 equals to 8,000 meters. Let's just put it almost Everest altitude. Okay, so if you do that, if you put that y2 here, therefore p2, if you substitute in that equation, it's going to be around 0.399 atmospheres. You can do the calculation. Let's just say I use these numbers, 9.81 meters square seconds, and R was equal to 286 joules kilogram Kelvin. Okay, so that's what I used for this ideal gas called air. So this one is for air. That's important. I'm not taking in consideration a lot of things like what's in the atmosphere. I'm just saying it's just air. So you will get, with this is the pressure, okay? So it needs to be lower than 1 atmosphere. So that's what this equation over here, well, this same one, it's telling me, okay? So it's actually giving me numerical results that are valid. Okay, I don't know if they are really accurate, but it seems to be at least logical in the sense that it's going as you go up. Okay, so the value is going down for pressure. That makes sense. Now let's just add another, let's just say KC. So this KC, it's another complication or a little bit, let's just make a realistic picture with this one. We still start with this, okay, minus rho g. I'm going to say, well, you know what? This is not a constant anymore. G is still a constant, but now I'm going to say, you know what? Temperature is not a constant. Okay, I'm going to say, well, you know, temperature is, and I forgot, guys, this is important because another value that I should have here is that T, the one that I use is 298 Kelvin. Okay, those are the values that I used. Sorry about that, that thing that I just missed there. In this case, I will not say that this one is two. So this one is not just one number, it's gonna change, okay? So this is the thing that I'm taking here. I'm gonna take, you know, this is temperature and this is altitude. So I'm gonna take, you know, this y positive, and I'm gonna say, well, you know what, when this thing is 0, I'm gonna take that this is around, I'm gonna put it here just for the sake of visibility. So when I'm looking at sea level, I'm saying, well, you know what, it's 25 degrees Celsius, 298 Kelvin. But when I'm gonna go, okay, over here, let's just say 11,000 meters, which is kind of, it's just a limit called tropopause, or it's the limit of the troposphere. Okay, so then you have really cold temperatures. Okay, so I'm gonna say this is minus 55 degrees Celsius or something like that. Therefore, what I'm going to take here, I'm going to put it around 288 Kelvin. Okay, so that's what I'm going to pick here, the 18 Kelvin. Okay, so that's what's going to happen here. So this over here is just a gradient, okay? It's the profile of temperature within the troposphere. So from here, meters, 0 meters to 11,000 meters is just the troposphere. So that's a little bit, this is a linear relationship of temperature whenever you go up, okay? So just the troposphere. Then you have here the stratosphere, and then you have other layers of the atmosphere. But the one that we are interested about right now is this one. Therefore, you have a straight line as a function of temperature. So this one is just a function of, I'm sorry, not a function of temperature, but the temperature is now a function of the altitude. Okay, so the basic idea here that I'm looking for is I want to find an expression for this temperature so that I can put it here. So I'm still gonna use this PRT, but this temperature is not longer gonna be a constant. Therefore, what I'm gonna try to find is this one over here. It's not very difficult since I already have 2 points, right? So I have point 1 and I have point 2, and you can put it here. So point 1 is temperature T1 equals to 298 Kelvin when Y1 equals to 0, and for 2 I have T2 equals to 218. That's the value that I used. You can change it a little bit more, or it's gonna be minus 50 degrees, minus 60 degrees. Okay, so it's not very complicated. And in Y2, I'm gonna put 11,000 meters. I want to use meters. I could use kilometers, but maybe it's gonna ruin up whenever I'm gonna put something here with the units. So I'm still gonna put meters. So with this, you have 2 points, and then you can perform the equation of a straight line. I'm gonna get the m, and the m is just the well, it's the slope of this line, and you already know this one, x2 minus x1. Sorry about this, but this y over here is just a generalization of the formula, but y, it's my x-axis. Sorry about that. So I should put t2 minus t1 because that's the y part, and this one is x part. So sorry about that confusion. I'm using y for the altitude, and that's kind of mess up a little bit. But okay, so m, if you substitute here, I'm gonna just go ahead and do this a little bit more quickly. So it's 7.272 times to the minus 3 degrees Celsius per every meter that you go up. Okay, so that's the slope. And then therefore, I'm going to get the T equals to minus 7.272 times to the minus 3, multiplying the altitude Y plus 298. And 298 is a value of the temperature when y equals to 0. Okay, so that's that. This one is a little bit simple to see. This one is you need to do a little bit of calculation to get. That's my temperature. I'm just gonna write it like this: my plus b. Okay, because I don't want to write the whole thing, but you already know what's the expression of this function. So now that I have here, I have this expression, so I'm going to substitute it over here. Therefore, my complete equation would look like this. So dp divided by dy equals to minus, okay, let's be a little bit more careful, p divided by r, and then my plus b, okay, so that's the equation, multiplied by, let's see if I'm missing something. Yeah, I'm missing g, okay, and that's it. So now I need to separate variables, and you know the drill. So dp divided by p equals to minus, let's just see what the hell is going on there, minus gr, and then I'm going to put dy over here, and then my plus b. Okay, so let me just protect myself with a parenthesis, and then I'm going to do this integral. Okay, so now I have everything that I need, and the only thing it's missing here is how I'm gonna do this integration part. This integration part is not very difficult. The left side part we have already done it, so I'm gonna write it here. Therefore, this one is just logarithm of p2 divided by p1. Okay, so that one is no problem. And then I'm gonna do this minus gr, and then the integral of dy divided by my plus b. So this integration is not very difficult, but I need this m here. Otherwise, this thing's not going to work. And if I put an m, which is the constant, okay, or it's just the slope, if I put an m here, so I have already this. So let's just say u equals to my plus b. And if I differentiate this one, it's going to be m dy. Okay, if I do that, therefore, this is the thing that I'm looking for. I want to put a du over there. So in order to an m appear here in the numerator, I need to put it over here. That's the thing that I'm going to do it. And therefore, I'm going to write it here. So logarithm of p2 divided by p1 equals to minus g mr. Okay, and so I'm just going to do this integration because it's already set up for doing this, minus g mr integration of du divided by u. Okay, so this one is just a logarithm. So logarithm of u2 divided by u1. That's going to be, it's going to be from u1 to u2. Therefore, this is a logarithm. So this is a logarithm, m y2 plus b m1 plus b. So this is u2 over here, and this is u1 here. And I don't know if you remember, but y1 was equals to 0. Therefore, this thing simplifies a little bit more with just logarithm of p2 divided by p1 equals to minus g. For the guys that already know how to integrate this, so sorry, but let's just put everything into context. my2 plus b divided by p. Okay, so a little bit more simplified. And I can get rid of this logarithm. So I'm going to do it. Therefore, this thing is going to be p2 divided by p1. Apply the exponential function in the left side. So I'm going to apply the same thing here. I don't know if you know about the properties of logarithms, but I can put this one as an exponent. Here's the power here that it's happening there. Therefore, I'm going to put it, and then with exponential part, I will just get rid of this logarithm. So this thing just stays like my2 plus b divided by p, and then everything has this power, minus g mr. So that's the power of this stuff. You know everything. I mean, P1 equals to 1 atmosphere, B equals to 298 Kelvin, M equals to 7.272 times minus 3. It was, sorry, this is wrong. I should put a minus there because the slope is a negative slope. Okay, so it's a minus. So whenever you see M, it's going to be a minus, but this one is degrees Celsius. And then, I'm sorry, this is not degrees Celsius. This is Kelvin because I work everything with Kelvin and then meters. So this is wrong, guys. Let me just put it here. Wrong. This is not degrees Celsius. This is Kelvin. I work everything with Kelvin. Otherwise, it would be a problem because this guy has Kelvin as units. Okay, so now I have everything in place. You know, G equals to 9.81 square. Oh my God, I just forgot about these units. So I think these ones are the units of acceleration. This is the only thing that's going to change. This y2 is just, okay, let's just see how much you want to put that. So if you can do the calculation. So if you put, let's just put it here. So let's just put y2 equals to 8,000 meters, Everest-like altitude. Therefore, if you have this, P2 is going to be equals to approximately 0.3589 atmospheres. So it's going to change a little bit from the B case. Remember B case? So B case was around here. So this is B case when the temperature was constant. And this is just, I wouldn't say a bad approximation, but not the most accurate. This one is most accurate approximation, or you could say that it resembles the real pressure over there. Okay, so now you have this equation for this case, okay? And I have put here this curve. So this curve is the comparison of case B and C, okay? So this is KB and this is case C, okay? So the B is the blue line, and this blue line is telling me something when the temperature is constant, and the orange line is telling me when the temperature is changing with the profile that we saw in the troposphere, okay? So it's not very, they are not very dissimilar. They start to deviate apart a little bit when you go to 4,000 or 4 kilometers around there. And if you are, I don't know, here, well, you have, yeah, like, I don't know, 10%, 15% of, or maybe less than that, of deviation. But this one could be the real part over here. This one's going to be the real part. But the blue line is not very far away. So if you're going to do estimations, you can say, well, the temperatures could be constant for a certain altitude, okay? But if you're going to do more accurate calculations, therefore you should use the orange line, but you already have the expressions for all those three ones, okay? So that's it for today, guys. I will see you later.